You know, we've spent a good amount of time here exploring the amazing things modern language models can do, writing, translating, coding, you name it.
Absolutely incredible capabilities.
But have you ever paused to think about why a model produces a specific answer? It can feel a bit mysterious.
Definitely.
Only
Especially when you consider the sheer scale of the data these things learn from.
trillions of tokens. That's words and pieces of words. I mean, it's a truly staggering amount.
Yeah, mind-boggling.
Trying to pinpoint where a particular phrase came from and all that, it seems almost impossible.
It really does feel like searching for a needle in a haystack, a continent-sized haystack.
Or maybe a drop in the ocean, yeah. With data sets of that magnitude, just grasping the broad learning patterns is a huge task, let alone tracing the origin of like a specific sentence or even an idea. Well, hold on to your hats because researchers at the Allen Institute for AI and the University of Washington have just launched something called OLMOTRACE.
OLMOTRACE.
Okay. And this is pretty wild. It's the first system that can actually trace a language model's output directly back to its entire multi-trillion token training data.
Wait, the entire data set.
The entire thing.
Yeah.
And it can do it in what feels like real time.
Real time for that scale. Wow, that's a bold claim. How is that even achievable?
Okay, let's unpack this. So imagine the language model gives you an answer.
Right.
OLMOTRACE takes that answer and then digs through its entire learning history, all those trillions of tokens, to see if that exact sequence of words appeared anywhere in there.
So verbatim matching.
Exactly, verbatim matching. And when it finds a match, it shows you the document where it found it. Think of it as like an incredibly powerful, super specific search.
But not of the internet?
No, not the internet, but of the LM's entire past learning experience, its own memory, so to speak.
And it can do this very quickly. You said real time. The research mentions something called infini-gram and results in seconds.
Yeah, infini-gram. That seems to be the key.
What's the secret sauce behind that speed then?
As I understand it, the key is how they've organized and indexed all that training data beforehand.
Ah, pre-processing.
Right. They use this infini-gram technology, which is apparently a really efficient way to essentially pre-sort all the possible endings of all the text in the training data, like every possible suffix.
Okay, so everything's lined up alphabetically, kind of.
Conceptually, yeah. So when you feed OLMOTRACE a bit of the LM's output, it can very rapidly locate any exact matches within this massive pre-sorted index.
That makes sense.
And they've also come up with some clever ways to do many of these searches at the same time, in parallel. That speeds things up even further.
So it's all about being incredibly organized with the data to make finding what you need lightning fast. That makes perfect sense. And what's the big picture here? Why build something like OLMOTRACE?
The researchers explain that it's all about gaining a deeper understanding of how these language models behave.
Peeking under the hood a bit more.
Exactly. They want to give us a way to see where these models might have encountered specific phrases or ideas during their training.
Which could be super useful for, what?
Yeah.
Fact-checking.
Yeah, that's a big one. Checking if something a model says is actually, based on its training data.
Or maybe figuring out why they sometimes hallucinate.
Could give us clues, definitely. And even insights into where the model's apparent creativity might come from. Is it really creative or is it echoing something?
Interesting. So if OLMOTRACE finds an exact match in the training data for something the model presents as a fact, what does that tell us? Does that automatically confirm it as true?
Good question. And not necessarily. The researchers are very clear about this.
Okay.
Just because a particular phrasing exists in the training data doesn't automatically make it reliable or accurate. It just means the model saw that sequence of words before.
Right. The source could be anything.
Exactly.
Right.
It could be a well-researched article, or it could be like a random comment on a forum or a personal blog.
So OLMOTRACE gives you a starting point, a link back to the data.
And then you can investigate the context of that match in the training data yourself, allowing you to make a more informed decision.
That's a really important distinction. It's a tool for exploration, not like a final arbiter of truth.
Precisely.
Now, you mentioned this is available for anyone to use.
Absolutely. It's open source, which is great.
Yeah.
And you can access it through the AI2 Playground. The web address is playground.alani.org.
Playground.alani.org.
Got it. You can go there right now and try it out for yourself.
That's brilliant. Getting hands-on with these kinds of tools is always the best way to really understand them. And which models does it work with currently?
Right now, it supports the three main OLMO models,
Okay.
including the OLMO 232B Instruct model, And it searches through the entire training data for each of these models.
The whole history, pre-training, fine-tuning, everything.
Everything. All the data they were trained on, from the very initial pre-training stages all the way through any later mid-training fine-tuning or instruction tuning they might have undergone.
Wow. So you can essentially see the complete data history behind the outputs of these specific models. Okay, we've covered what it is, why it's important. Now, let's dig into the mechanics a bit.
Sounds good.
At a high level, how does OLMOTRACE take a language model's response and, generate these tracing results for us?
Okay, so you basically paste in the text that the language model produced, right? The output.
Yep.
The system then gives you back two main things. First, it highlights the specific sections, the spans of that generated text that it found as exact matches within its training data.
Visually highlights them.
Yeah. And second, it provides a list of the actual documents from the training data where those highlighted phrases appeared.
And you can see the documents themselves, or snippet.
Usually snippets, yeah. Little snippets of the document surrounding the matching text. Sometimes even links back to the original source, if it was web data.
The paper mentions Figure 1 on the AI2 playground shows this visually. It sounds like a very user-friendly way to see the connections.
It seems designed to be pretty intuitive.
And you mentioned that the speed comes from pre-sorting all the suffixes of the training data using infini-gram. Can you explain a bit more about why that's such an efficient method for finding those exact matches quickly?
Right. So imagine you have this massive list of every single way every sentence in the training data ends, or every sequence.
Every suffix.
Every suffix, exactly. Now, imagine that list is perfectly alphabetized.
Yeah.
Finding a specific phrase becomes much faster because you can use that alphabetical order to quickly jump to the section where your target phrase would be, if it exists. You don't have to scan linearly.
Like a binary search, but way more complex.
Kind of, yeah. infini-gram does something conceptually similar, but at a much more advanced level, using suffix arrays, allowing for incredibly fast lookups of exact sequences of these tokens, which are the text building block.
And the parallel algorithms you mentioned earlier.
Right. They also use parallel processing, so they can do many of these suffix lookups simultaneously, which significantly cuts down the overall time.
The paper mentions an average tracing time of around 4.5 seconds for a typical 450 token LM response, which is really impressive considering it's searching through trillions of tokens.
It's kind of mind-blowing, really.
And it's worth emphasizing again, OLMOTRACE is specifically looking for verbatim matches, exact sequences of words.
That's right. It's focusing on the most direct, undeniable link between the output and the training input. No interpretation, just, was this exact sequence seen before?
Got it.
And it's not just a one-way search either. The system has interactive features.
Oh, like what?
Well, you can click on a highlighted section in the LM's response.
Yeah.
And instantly see which training documents contain that exact phrase.
Cross-referencing.
And conversely, if you're looking at a specific training document snippet it shows you, you can see all the parts of the LM's original response that match something in that document.
That interactive aspect sounds incredibly valuable for really digging in and, understanding the relationships. It's not just a static report.
Exactly. Lets you explore.
Okay, let's get a bit more into the nitty-gritty now. The paper describes a 5-step process OLMOTRACE follows. Let's walk through those.
Okay, step by step.
Step 1 is find maximal matching spans. What exactly does that involve?
So in this initial step, OLMOTRACE looks at the LM's generated text and tries to find all the longest possible continuous sequences of tokens
Longest possible.
that appear exactly as they are somewhere in the training data.
Okay, and there are criteria.
Yeah, a few. First, obviously it has to be an exact match in the training data. Second, it needs to be self-contained,
Meaning?
meaning it shouldn't typically break in the middle of a sentence unless it's right at the end, like with a period, and it shouldn't start or end with incomplete words.
Got it. Clean boundaries.
Right. And the third criterion is maximality.
Maximality. What does that tell us?
Maximality means the sequence they find shouldn't just be a smaller part of an even longer sequence that also meets the first two criteria. They're aiming for the longest possible valid matches at each point.
So if the quick brown fox is a match, it won't also report quick brown separately if it's part of that longer match.
Exactly. It avoids redundancy. The paper mentions that finding all these naively could be computationally brutal,
I bet.
but they've developed a much faster algorithm using that infini-gram tech to handle this efficiently.
Right. They mentioned reducing complexity significantly. Okay, so after identifying these maximal matching spans, step 2 is filter to keep long and unique spans. Why filter?
Well, think about it. If every tiny little common phrase like is a or and the that appeared in the training data was highlighted.
It would be useless noise.
Totally overwhelming, yeah. It wouldn't give you any meaningful insight. So this filtering step is designed to focus our attention on the more significant matches, the ones that are likely to be more, well, interesting or informative.
And how do they decide what's interesting? They use something called span unigram probability. Can you break that down?
Okay, so for each of those maximal matching spans they found, they calculate how likely that specific sequence of tokens is based on how often each individual token, each word or subword, appears in the entire training data set.
So frequency of the parts.
Right. If a span has a very low unigram probability, it means it's either relatively long or it contains words that are quite rare in the training data overall, or both.
Lower probability means more unusual.
Exactly. Less probable means longer and more unique. These spans are considered potentially more insightful.
So a common phrase like "thank you very much" would probably have a higher probability and might get filtered out.
Right.
While a longer, more specific technical term or a unique tuna phrase would have a lower probability and be more likely kept. That makes sense for usability.
Yeah, the paper mentions keeping the top K spans with the lowest unigram probability, where K is like a small percentage, maybe 5% of the total length of the LM output in tokens.
And they found this worked better than just keeping the longest ones.
Apparently, yes. They mentioned they tried just keeping the longest spans initially, but using this span unigram probability metric actually led to retrieving more relevant documents later on. It was a better predictor.
Interesting. Okay, so after filtering for these interesting spans, step 3 is retrieve enclosing documents. What happens here?
So for each of those filtered spans, the longer, more unique ones kept from step 2, the system then goes and fetches snippets from the training data.
Snippets of the documents containing that exact span.
Exactly. It retrieves up to 10 document snippets that contain that exact sequence of words.
Why up to 10?
They say because of that maximality requirement from step 1, most of these filtered spans actually don't appear that many times in the training data, often 10 times or less.
Ah, because they're long and specific already.
Right. But if a span does happen to occur more often, they just take a random sample of 10 to keep the results manageable and avoid flooding the user.
Makes sense. Then step 4, merge spans. Merge documents. Sounds like tidying up the display.
Precisely. Just cleaning things up. If there are multiple highlighted spans in the LM output that actually overlap each other,
Yeah.
they get combined into a single, larger highlighted span in the display. Makes it less cluttered.
And similarly for documents.
Yep. If the system retrieves multiple snippets that all actually come from the same original training document, those are merged into just one single entry in the document panel. Avoids showing the same source multiple times for different parts of the same match.
Good interface design. Finally, step 5, re-rank and color documents by relevance. How does it figure out which documents are most relevant? It found maybe 10 snippets per span.
Right, you could still have quite a few documents listed.
Yeah.
So this is where they use a standard technique from information retrieval
Yeah.
called BM25.
BM25, heard of it, used in search engines, right?
Exactly. They essentially treat all the retrieved document snippets as a small collection, like a mini database.
Okay.
And then they use the original prompt you gave, the language model, plus the model's full response as the search query against that collection.
Ah, so they're asking, which of these retrieved training snippets is most related to the overall conversation topic?
Pretty much. The BM25 algorithm calculates a relevant score for each document snippet based on how well it matches that prompt plus response query. And the researchers found these scores actually line up quite well with how humans would judge the topical relevance.
Okay, so higher BM25 score means more topically relevant to the query, and the coloring helps visualize this.
Exactly. They take those scores and group them into 3 levels: high, medium, and low relevance.
Medium, low, simple.
And these levels are shown by different colored bars next to each document in the panel, like maybe red for high, yellow for medium, gray for low, something like that.
That's visual cues. Nice.
And importantly, the highlights back in the LM's output text are also colored. They take the color corresponding to the highest relevance level of any document that contained that specific highlighted span.
Oh, that's clever. So you can glance at the highlighted text and immediately get a sense of whether it likely came from a highly relevant source document or a less relevant one.
Right. Helps you prioritize where to look first. It connects the relevance back to the specific matched text.
That's a really well thought out process. Taking this incredibly complex tracing task and presenting it in a digestible and useful way.
Seems like it.
Now let's dive a bit deeper into what's happening behind the scenes, especially this infini-gram technology. That speed is still pretty amazing. You mentioned it uses a suffix array. What exactly is that, and why is it so good for this?
Okay, so infini-gram is described as a text search engine built specifically for these like planetary scale data sets, trillions of tokens.
Purpose-built.
Yeah, and at its core, it uses a data structure called a suffix array. Now imagine taking every single possible ending or suffix starting from every position in every document in the training data.
That's an astronomical number of suffixes.
Huge. And then putting all of those suffixes into perfect alphabetical order. That ordered list is essentially the suffix array.
Okay, an alphabetically sorted list of all possible text endings.
Right. And this pre-sorted structure allows for extremely efficient searching. Instead of having to scan through the entire data set linearly for a specific phrase.
Which would take forever.
Exactly.
Yeah.
You can use the alphabetical order, like a binary search, to very quickly pinpoint the range in the array where that phrase, or any phrase starting with the same sequence, must reside if it exists.
Super fast lookups.
That's the idea.
And the paper mentions this huge suffix array index isn't kept in RAM, but on SSDs, solid-state drives.
Yeah, because the index itself is massive. Trillions of tokens generate an enormous suffix array. Way too big for the main memory, the RAM, of even monster servers.
So it has to live on disk. But SSDs are fast disks.
Right. They store it on fast solid-state drives, which are much quicker than old spinning hard drives. This allows the system to fetch the necessary parts of the index from the SSDs relatively quickly, without a huge bottleneck.
Did they keep anything in RAM?
Yeah, they mentioned keeping some crucial metadata in RAM, which acts like a map or an index to the main index on the SSDs to speed things up even more.
Gotcha. The paper also talks about a parallel algorithm for finding those maximal matching spans. It focuses on finding the longest matching prefix of each suffix of the LM output. Can you walk through that using the find queries in the infini-gram?
Right. This is how they actually implement finding those spans from step 1. So, for every single possible starting point in the language model's output text,
Yeah.
you can think of the rest of the text from that point onward as a suffix of the output.
Okay.
OLMOTRACE needs to find the longest sequence at the beginning of that suffix, its longest prefix, that also exists exactly somewhere in the training data's suffix array.
How does it find that longest prefix efficiently?
infini-gram has this core operation called find. You give it a search term, like the whole suffix in the LM output. Find then looks it up in the giant suffix array on the SSDs.
And returns.
It returns the section, the range, within the suffix array that corresponds to all the locations in the training data where that exact search term appears.
Okay, but what if the exact suffix isn't in the training data, which is probably common?
Good point. And here's the clever bit. If the exact suffix isn't found, find still tells you where it would have been in the sorted suffix array.
It's hypothetical alphabetical position.
Exactly. And the suffixes in the training data that are immediately before and after that hypothetical position in the array are the ones that are alphabetically closest to your search term.
Ah, the nearest neighbors in the sorted list.
Right. By comparing your search term, the LM output suffix, with these two neighbors, you can figure out the length of the longest initial sequence they all have in common.
And that common sequence is the longest matching prefix that exists in the training data.
Precisely. It's a really neat trick using the sorted nature of the suffix array. And it means you can find the longest match without having to try lots of different lengths. Just one find operation per starting position in the LM output.
That is very clever. And because each starting position, each suffix of the LM output can be processed independently.
They can run these find queries in parallel for all starting positions simultaneously. Big speed up.
The paper also mentions sharding the infini-gram index, breaking it up.
Yeah, because even with SSDs, a single index for trillions of tokens is just too unwieldy to manage efficiently.
Too big for one machine or one process.
Right, so they break the massive suffix array down into smaller, more manageable chunks called shards. The paper mentions a limit, like maybe 500 billion tokens per shard.
Okay.
When they perform a find query, they actually run that query in parallel across all the shards at the same time.
And then combine the results.
Basically, yeah. They find the longest matching prefix found in any of the shards. And they mention they run a second find query right after the first one.
Why a second query?
The first find just determines the length and content of the longest matching prefix. The second find query, using that identified prefix, is apparently needed to efficiently locate all the occurrences of that prefix across the shards, which helps with accessing the data quickly from the SSDs, maybe using disk caching effectively.
Okay, makes sense. Find the match, then find all locations of the match. And finally, after finding all these longest matching prefixes for every starting point, they need to filter out the non-maximal spans, right? Step one's maximality criterion.
Correct, because the process we just described finds the longest match starting at each position. You might find that the match starting at position 5 is brown fox jumps, and the match starting at position 7 is fox jumps over. The second one is contained within the first one's span, if you consider where they start and end.
So you only want brown fox jumps in that case.
Exactly. You want the one that extends furthest. So they essentially go through the list of found spans, ordered by their starting position in the LM output. They keep track of the ending position of the last span they decided to keep. For the next span in the list, they only keep it if its ending position goes beyond the previous kept span's end.
So only keep spans that push the boundary forward.
Right. This simple pass ensures they are only left with the truly maximal spans, the ones that aren't just subparts of other longer spans starting earlier.
A clean filtering step. Okay, that's a really thorough look at the mechanics. Very impressive engineering. Now, let's move on to the case studies they shared. These really show the value.
Yeah, the practical examples.
First one, fact-checking. How did they illustrate that?
Okay, they use the example of the Olmo model saying something like, the Space Needle was built for the 1962 World Fair, a factual statement.
Right.
When they ran this through OLMOTRACE, the system highlighted that whole phrase, found it as an exact match in the training data.
And showed the sources.
Yeah, showed the documents where it found it.
Yeah.
And they note that, especially for the pre-training data, which often comes from the web, these documents often include a URL back to the original web page.
So you can click through and see the original context.
Exactly. In the Space Needle case, seeing the source and the context allows a user to verify, okay, yes, this statement appears in seemingly reliable sources the model was trained on. It helps ground the model's claim.
So if you ever wonder, did the model just make that up or did it see it somewhere? OLMOTRACE can potentially show you where it might have seen it.
Right. It gives you a lead to investigate.
Okay, second case study. Tracing creative expressions. This is really interesting. How can you trace something that seems novel?
Yeah, this one's fascinating. The researchers make the point that even language that feels original or, creative coming from an LM might actually be based on specific word combinations or patterns it picked up during training. Not necessarily deep understanding, but pattern matching.
Okay, makes sense. What was their example?
Their example was getting Olmo to generate text in the style of Tolkien.
Yeah.
And the output included the phrase, I'm going on an adventure.
Ah, very Bilbo Baggins. Seems creative in context.
Exactly. But when they used OLMOTRACE, guess what?
It found a match.
It found an exact match for I'm going on an adventure in a piece of fan fiction about the hobbits that was in the training data.
No way. Fan fiction.
Yep. So what feels like a spark of Tolkien-esque imagination might have actually been the model directly echoing a phrase it saw in related but perhaps unexpected training material.
That's quite revealing. It really suggests that what we perceive as creativity could sometimes be sophisticated mimicry or recombination of memorized chunks.
It definitely complicates the picture of LM creativity, doesn't it?
Really does. Okay, third case study. Tracing math capabilities. How does OLMOTRACE shed light on how LMs learn arithmetic or problem solving?
This one's also pretty eye-opening. They had almost solve a combinatorics problem from a math competition, the AHE exam, and it got the right answer.
Okay, impressive.
But then they used OLMOTRACE on the model's reasoning steps, and it found that the crucial calculation step,
The actual math part?
yeah, the formula like n choose k equals n over k times nk, and the specific numerical result like 2, 10, that exact string
Yes.
was found verbatim in the post-training data set. Possibly data used for instruction tuning or alignment.
Whoa, so didn't necessarily calculate it dynamically?
It suggests it might have just retrieved a memorized calculation step that matched the context of the problem.
So it might look like reasoning, but under the hood, it could be retrieval of a specific learned instance.
Exactly. It makes you really rethink what solving or understanding means for these models when you see this kind of direct tracing back to the data.
Yeah, absolutely. It highlights the importance of looking at the training data to understand the how behind the model's abilities, not just the what.
Couldn't agree more.
Now, the paper also makes some important distinctions between OLMOTRACE and other related concepts or technologies. Let's clarify those.
Good idea.
First up, how does OLMOTRACE differ from RAG retrieval augmented generation? That also involves retrieval.
Right, but the key difference is when and why the retrieval happens.
Okay.
Archaea systems typically retrieve relevant documents before the language model generates its response.
To give it information.
Exactly. Those retrieved documents are fed into the model to inform or ground the generation process itself. It's about improving the output by giving it current or specific knowledge.
Right, augmenting the generation.
OLMOTRACE, on the other hand, does its retrieval after the LM has already generated its output.
Post-generation analysis.
Yes. Its purpose isn't to influence or improve the generation, but rather to understand it, to show the connection between the text that was already generated and the data the model was originally trained on.
That's a really clear and important distinction. RAG is for making the output better. OLMOTRACE is for understanding the output's origins.
Well put.
Okay, another comparison. Traditional search engines like Google or Bing.
Yeah.
How is OLMOTRACE different?
Well, search engines index, the vast public web,
Yeah.
mostly, and they rank or filter results based on all sorts of complex algorithms, relevance, authority, maybe even ads.
Right, they're trying to find the best answer from the web.
OLMOTRACE isn't searching the live web. It's searching a static, closed data set, the specific training corpus of a particular language model.
The model's internal knowledge base.
Exactly. And its goal isn't necessarily to find the best match, but to find all verbatim matches within that specific data set, without external filtering or ranking, just showing what's there.
So different scope, different goal. Got it. And finally, they position OLMOTRACE relative to other methods for tracing LM generation, like influence functions.
Yeah, they contrast it a bit. Methods like influence functions try to figure out which specific training examples had the most mathematical impact on a particular output by analyzing gradients or how the model changed during training.
Sounds computationally heavy.
Extremely. Especially for trillion-token data sets. They say it's often impractical right now. Influence functions try to estimate a sort of causal link based on the learning process.
Whereas OLMOTRACE is more direct.
Yes, OLMOTRACE takes a much more direct and computationally feasible approach by focusing on that simple, undeniable lexical overlap, the exact word-for-word match. It's less about influence during training, more about presence in the training data.
Okay. And they also mention other tracing ideas, like models citing sources.
Right, they briefly mention other approaches people are working on, like training LMs specifically to cite sources as they generate text, or using external search during inference to find support. OLMOTRACE is distinct because it's a post-hoc analysis tool focused purely on the original training data connection.
Okay, that context is helpful. Now, before we wrap up, it's crucial to touch on the limitations and considerations the researchers themselves point out.
Absolutely. Need to be careful how we interpret these results.
What are the main caveats?
Probably the most important one is that just because OLMOTRACE finds a verbatim match,
Yeah.
it does not automatically mean that the training document caused that output, or that the training document is a valid citation or proof for the output's claim.
Correlation isn't causation.
Exactly. It just shows the model encountered that exact sequence of words. The model might have generated it for completely different internal reasons, or the original source might be unreliable. It's an indicator of exposure, not necessarily direct sourcing or validation.
That's a vital takeaway. Just because the model repeated something it saw doesn't mean it knows it in a deep way or that the source was good.
Right. Don't overinterpret the match as proof.
Anything else? Any potential downsides?
They also acknowledge that because OLMOTRACE surfaces content directly from the training data, it could potentially expose problematic content that exists in those massive data sets.
Like what?
Things like copyrighted material that maybe shouldn't have been in there, private or personal information, toxic language, biases. If in the training data, OLMOTRACE could potentially highlight it if the model outputs it.
So it could inadvertently reveal issues with the training data itself.
Could do, yeah. It's a transparency tool, and sometimes transparency reveals uncomfortable things.
Important points to keep in mind when using it.
Definitely.
Well, as we start to wrap up this deep dive, it seems pretty clear that OLMOTRACE is a really significant step forward.
Oh, absolutely. A major advance in our ability to sort of peek inside the black box of these huge language models.
It really is. For the first time, we have a practical tool to trace model outputs back to the actual massive data sets they learn from.
And to do it fast enough for real investigation. That's key.
Yeah, that real-time aspect is huge. This has massive potential for researchers, developers, even the public, to get a much better handle on how these models actually learn and generate text.
And it gives us a concrete way to explore that link between the training data and model behavior, right? Whether we're looking at factuality
Or apparent creativity.
or even specific skills like solving math problems.
Yeah.
We can see the data connection now or lack thereof.
And as you mentioned, people can try this themselves. OLMOTRACE is live on the AI2 playground.
Yep, https://playground.alani.org. Go check it out. It's fascinating to play with.
It really sounds like a fantastic opportunity to see this tech in action.
So here's maybe a final thought to leave everyone with, something to chew on. Given that OLMOTRACE shows us that even things that look like creativity or complex reasoning can sometimes be traced back to verbatim chunks in the training data, what does this really tell us about the nature of, language model understanding or intelligence?
Does it change how we think about model intelligence if so much can be linked back to memorization or sophisticated pattern matching?
Right. And what new questions does this ability to trace outputs actually unlock for future research, or even just for how we interact with and trust these incredibly powerful and sometimes baffling technologies?
It certainly gives us a lot to think about, a powerful new lens to view these models through.
Definitely does. Lots to ponder there.